You've seen this scene in every TV police drama. The forensics team dusting a crime scene for fingerprints. Everyone's fingerprints are slightly different, which makes them incredibly useful for determining who's touched what. Even though everyone's fingerprints are slightly different, they still fall into three main types of pattern: loops, arches, and whorls. However, arches are relatively rare, so we're going to group them in whorls for this experiment. We're here to find out whether men and women have different types of fingerprint patterns.
We're going to take as large a sample of men and women as we can and see what pattern type they have on their right index finger. Then we'll perform a chi-squared test to see whether sex and fingerprint type are independent, or whether knowing one thing tells you anything about the other. Both sex and fingerprint type are categorical variables. You place things in categories like your eye colour or where you were born. Things like your height and weight are continuous variables, things that you measure. Numerical variables, such as the number of siblings you have, are somewhere in between. Sometimes they can work like categorical variables, or sometimes they can work like continuous variables. You can have 2 siblings, but not 2.5. One of the tests that you can use to see if 2 categorical variables are related to one another is called a chi-squared test of association. It can't tell us the answer for certain, but it can tell us how unlikely it would be to get similar observations by chance alone.
Now, the first thing we do with any statistical test is set up the hypotheses, the conclusions we can draw from the experiment. There are 2 for the chi-squared test. The first, the null hypothesis, and our default answer is that the variables are independent. In this case, the null hypothesis is that knowing someone's sex doesn't tell us anything about how likely they are to have a particular fingerprint type and vice versa. This is the conclusion we'll draw unless we have strong evidence on the contrary. The second hypothesis is the alternate hypothesis. This is the other possibility, that men and women do tend to have different fingerprint types. In this case, we would say there is an association between a person's fingerprint type and a person's sex. The next question is, how strong should the evidence be before we reject the idea that the variables are independent? The significance level is a value we choose. It's normally 0.05. That means if the probability is a more extreme result than the one we come up with, less than 5%, we reject the null hypothesis and accept the alternate. Otherwise, we say we don't have enough evidence to reject the null hypothesis. Okay, now let's get some results.
Index finger on the pad. Yes, that's a loop. Thank you. Just in.
That's a loop.
There. Oh wow, second arch of the day.
It's a loop. You have a loop.
Okay, we've collected all our data on fingerprint type. Next, to do a chi-squared test, we set up a table like this one, a contingency table. We've got columns for our 2 main categories of fingerprint types, and 1 for the total. And we've got rows for each category of sex, and another one for the total again. Once we've recorded our observations, we put them into the obvious places. In our experiment, 10 of the women had whorls and arches, and 9 had loops. Among the men, 11 had whorls and arches, and 8 had loops. So, in the total boxes, guess what? We add up the numbers in the corresponding row or column.
From our data, it seems like women might be more likely to have loops than men. But is this due to random chance in our experiment? To find out, we also need to work out the expected value in each cell, which we get from multiplying the number at the end of each row by the number at the bottom of the column and dividing by the total. So for the women with whorls, that would be 19 times 21 divided by 38, making 10.5. These are the values that would be expected if the relative numbers of fingerprint type were exactly the same for both sexes. They are theoretical values and need not be whole numbers. Then we will work out the chi-squared statistic, which will tell us what conclusion we can come to. Today, we'll work it out using a basic formula here, although later on you might meet a Yates modification, which is often used for this 2x2 table. Oh, come on, it's not that bad. You don't have to remember it, you can look it up if you need to. Okay, so for each cell, we work out the difference between the observed value and the expected value, square it, and divide by the expected value. For men with whorls and arches, the difference is 0.5. We square it to get 0.25, then divide by 10.5 to get 0.024. Once we've done that for all the cells, we add it all up to get our statistic, which is 0.52.
We're not quite done though. We still need to see how the statistics stack up, and for that we'll need a lookup table. This example has 1 degree of freedom. It's 1 less than the number of columns multiplied by 1 less than the number of rows. So we look up the chi-squared table with 1 degree of freedom and compare our statistic to the 0.95 value. This is 1 minus our significance level of 0.05. If we picked a different significance level, we'd use a different value. The number we get for our critical value is 3.841.
Our chi-squared statistic is smaller than this, so we'd say we do not have significant evidence against the null hypothesis at 0.05 level. We'd conclude that there is not enough evidence to support an association between fingerprint type and sex. Don't worry if you can't reject the null hypothesis. This often happens. It's all part of the statistical process.
So, to recap, here are the steps required for a chi-squared test. Write down your hypotheses and choose a significance level of 0.05, unless you have a good reason not to. Collect your data and collate them into a table. Work out the expected value for each cell and use the formula to figure out the chi-squared statistic. Find the right table for your number of degrees of freedom and compare your statistic to the appropriate value in the table. Finally, decide whether to reject or accept the null hypothesis and write down your conclusion.
So that's it. Try it yourself and let us know how you get on.
Don't forget, you can learn more or download our free online resources at welcome.ac.uk/bigpicture.
Bye for now.